All right, let's kick off. Hi everyone, welcome to this seminar. Today we are going to cover AI inference serving frameworks. So the main goal of this seminar to help you better understand the key and popular AI inference frameworks, and also compare and just provide you an implementation plan so that you can use to just based on your use case or the types of workload, you can choose the right framework. So this is the agenda for today. So as you can see, we're gonna have a quick overview and provide you the context about the AI inference serving frameworks. Then we will dive deep in each of those serving frameworks, and then we will try to do more performance analysis and help you better understand and compare these different frameworks. And then we will conclude the session with some of these key takeaways. All right, let's start with the first section, which is more around the overview and context. So before we cover the key serving frameworks, let's talk about the core challenges involved in serving large language model. So LLMs can have billions or even trillions of parameters, which make them incredibly memory hungry. So just loading these large models onto GPUs is a task in itself, and let alone can run in hours, days, and even multiple hours. So one of the main hurdle here is that how these models generate text. So we got this self-regressive process, meaning each token that is generated by the model depends on all of the previous tokens. So to enable this, the LLMs usually use a key value cache that grows with the sequence length. So the longer the prompt or conversation, the more memory these KB or key value cache consumes. That creates serious memory management issues for running inference, especially when you are trying to serve multiple requests in parallel. And even to make it worse, we often pre-allocate memory to avoid the delay during generation. But this pre-allocation actually leads to fragmentation and underused GPU memory. On the top of all this, we have also need to juggle conflicting performance goals. User usually wants fast response times or low latency, but we usually aims for high throughput to maximize efficiency. So balancing these demands is a constant challenge in LLM inferencing. So when we talk about the LLM serving frameworks, it's important to understand that they're not all trying to solve the same problem. You can see this topology here, which actually break them down into three main categories, each serving a distinct role in the production stack. First, we have the high performance engine, things like vLLM and TensorRT-LLM. These frameworks are more like low-level libraries optimized to squeeze out the maximum performance from the GPU. They are all about fast token generation and efficient memory use, and those are usually ideal for scenarios where speed and throughput are critical. Then we have the orchestration layer, things like Triton and Racer. These tools and frameworks focus more on the MLOps side, things like request batching, load balancing, and managing model replicas. They are actually crucial for scaling LLMs in production and ensuring smooth operation under real-world traffic. And finally, we have all-in-one solution, things like Hugging Face TGI. These systems aim to simplify the entire deployment pipeline by combining model hosting, inference, and serving into a single platform. They are especially useful for teams that want to get up and running quickly without building the full stack. So the key point here is that these frameworks are not interchangeable. They each target different layers of the infrastructure, and understanding their role help you build a more efficient and also maintainable system. Now, one of the key architecture breakthrough in LLM serving is continuous batching. Traditional inference often relies on static batching, grouping requests into fixed size batches before sending them to the GPU. This works well when requests are uniform and also arrive in sync. But in real-world application, these are not the case. Requests usually vary in length and timing, which means static batching often leads to underutilized GPUs. So if the batch isn't full, or if some sequence finishes earlier than the others, you are wasting compute power. Continuous batching solves this by taking a more dynamic approach. As the new requests arrive, they are immediately added to a running batch. No need to wait for a full group to form. A smart scheduler keeps an eye on the queue and efficiently merges incoming prompt into the active GPU batch. This keeps the hardware busy and boosts the overall throughput, especially in high traffic or low sensitive environments. The other things that you need to be familiar is the concept of paged attention. So a major enabler of continuous batching in large language model is an innovation named page attention, which was introduced by vLLM. It tackles one of the most persistent issues in LLM serving, which is memory fragmentation. So the concept is actually inspired by how operating system manage virtual memory. Instead of requiring large continuous block of GPU memory for each request KB cache, page attention break the cache into fixed size block or pages. These can be stored anywhere in memory, and a logical lookup table maps them to the right physical location. This has several key benefits. First, it eliminates fragmentation, which is a common problem when handling sequence of different length. Second, it allows for more flexible and efficient memory allocation, since blocks can be reused and don't have to be lined up in memory. And third, it enables KB cache sharing. So if multiple requests uses the same prompt, they can share cache block instead of duplicating them. Page attention is a game changer for high throughput inference. It allows for smarter scheduling and resource use, making dynamic batching and also real-time generation at a scale much more feasible. Another concept that you need to be aware is the concept of speculative decoding, which is a clever technique designed to speed up inference without sacrificing the quality of generated text. It works by introducing a two-model workflow, a fast draft model and a large main model. The draft model, which is smaller and much quicker, generates a sequence of predicted tokens, essentially guessing what the main model is likely to produce. Then the main model steps in. But instead of the generated token one by one, it validates the draft sequence in parallel. If the main model agrees with the draft tokens, they are accepted and the process moves forward. If there is a mismatch, generation resumes from the point of divergence. This correction step ensures output accuracy, while the overall process significantly reduces the time spent on token by token generation. In practice, a speculative decoding can yield up to 3.5x faster inference, making a powerful optimization for real-time application where latency is critical. Another things that you need to be aware is the concept of quantization. So I'm sure majority of you is aware of this technique, which is also another optimization technique, especially when deploying at scale or on resource constrained devices. The idea is simple. You just reduce the numerical precision of model weight and activation to save memory and speed of inference. And as you can see, we have FP32, which is a full precision. Then you can have FP16, which is widely adapted actually today, which can get significant speed ups and reduce memory usage. Going further, we have FP8, which is another emerging as new standard for inference. And then at the extreme end is FP4, which pushes performance boundaries even further. There is always across all these different precisions, we have trade-off. So maintaining higher precision means you need to use more resources. All right, now that we cover some of these concepts related to these saving frameworks, let's start with the first framework, which is vLLM, which has quickly become a leading solution for high throughput LLM inference. So thanks to the smart architecture and also for user-friendly design, its core philosophy is very clear: deliver maximum performance and memory efficiency while keeping things simple and accessible. At the heart of vLLM, there are a number of innovations. We already covered the concept of page attention, which is actually at the heart of vLLM. Also on the top of that, vLLM incorporate highly optimized CUDA kernel and integrate with tools like flash attention and flash infer to push GPU efficiency even further. What's especially compelling is here is how easy it is to use vLLM. So it supports an OpenAI compatible API, means you can spin up a serving endpoint with just one command. Plus, it offers a flexible Python library for offline batch inference and also support both NVIDIA CUDA and also AMD ROCm, making it versatile across different hardware platforms. Also, you can use on AWS Trainium as well. So overall, vLLM brings cutting-edge performance and also practical usability. The next framework is NVIDIA TensorRT-LLM, which is the purpose-built engine for getting the absolute most out of the NVIDIA hardware. So here the core philosophy is all about deep hardware software code design, meaning tightly integrated with NVIDIA GPUs to maximize performance, especially through compilation-based optimization. The engine uses a Python API, and which is tailored specifically to the NVIDIA hardware. Another key feature is its robust support for low precision format, things like FP8 and FP4, which are crucial for high throughput memory efficient inference. It also implements a speculative decoding, the concept that we already covered, which is a smart algorithm enhancement for further accelerate generation without compromising output quality. So as mentioned, TensorRT-LLM fits seamlessly into the broader NVIDIA ecosystem. It also works with things like TensorRT Model Optimizer, allowing the user to perform quantization, pruning, and also some other optimization technology. Next framework is Triton Inference Server, which acts as a universal serving layer for AI model. Its system lies in its flexibility, which can manage and scale and route requests to model built with nearly any major framework or backend. At the core of Triton Inferencing Server, there is this decoupled backend architecture, which means Triton does not care what kind of model you are serving. You can plug in custom backend via a standardized CC+ API, which allow for deep customization and also extension. This makes it powerful option for complex or multi-framework deployment. Triton also is Kubernetes ready, which is ideal for modern containerized environment. It supports dynamic batching, which means it can group incoming requests in real time to maximize GPU usage. On the integration side, Triton is robust, which support HTTP, REST, gRPC, and also even Python-based integration with PyTriton. Overall, Triton is not just a model server, it's a fully featured production-grade platform for deploying and scaling AI at enterprise level. DeepSpeed Inference, which is designed for one thing, serving massive model, those with billions or even trillions of parameters. At the heart of the DeepSpeed Inference is Zero or Zero Redundancy Optimizer. So Zero actually partition model weight and state across multiple GPUs, so each device only holds a slice of the full model. DeepSpeed also support memory offloading, meaning it can push part of the model to host memory or even NVMe storage. It also combined with a suite of parallelism techniques, things like tensor parallelism, pipeline parallelism. So these are like some of these parallelism options for the models, and you can use DeepSpeed Inference for that. It also has custom optimized kernels which are designed to perform well even with small batch sizes. For ease of use, DeepSpeed also provide the MII repository, which includes high-level tools for deploying thousands of pre-optimized models. Next framework is Hugging Face TGI, which is designed to be a turnkey solution for serving LLMs. So its architecture includes three main components: a Rust-based router, a Python launcher, and also a model server. So the router is public-facing layer, which handles request scheduling and implement continuous batching to maximize GPU utilization. Then the Python launcher manage configuration and model loading, with the and then model server execute the model itself and communicate with the router via gRPC. Under the hood, TGI actually brings together several performance optimization. It integrates page attention from vLLM, support quantization for a smaller model, and also use safe and source for faster and also safer weight loading. On standout feature, there is this user-facing, especially for the user-facing application, there is this concept of token streaming, which TGI implement this using self-send event or SSE to stream token as they are generated. This actually drastically reduce perceived latency and also improve interactivity. Alright, the next framework is RayServe, which is built to be orchestration layer for complex scalable machine learning application. One of its key strengths for RayServe is Python native compatibility and composability, which means you can build sophisticated applications that combine multiple model data processing steps or business logic all in a way that feels natural to Python developer. It also supports fine-grained resource allocation, so each component of your app, whether it's a model, a router, or pre-post processing step, can scale independently. Combining that with auto-scaling, and the RayServe can dramatically adjust the number of replicas based on traffic. A popular deployment pattern is combining RayServe with LLM. This pairs Ray's orchestration and scalability with vLLM high-performance inference engine, giving you the best of both worlds, fast generation and also robust distributed architecture. RayServe also integrates smoothly with Fast API, Flask-side inference, and fits naturally into the broader Ray ecosystem. Alright, now let's quickly do some comparison between these different frameworks. So there is a benchmark which highlights the best inference framework, and here we are going to talk about vLLM and NVIDIA TensorRT-LLM. So one thing that you need to consider is that the best inference framework really depends on the specific performance goal, whether it's maximizing throughput or low latency responsiveness. In raw throughput test, TensorRT-LLM pulls ahead for short input-output scenarios. TensorRT actually delivers 1.34 higher throughput, which is aligned to the design philosophy because it's purpose-built for NVIDIA GPUs. But when we start to introduce this real-time constraint, like a strict 20 millisecond time per output token limit, the number change actually. Under this latency cap, vLLM actually outperformed TensorRT. So the takeaway for this benchmarking was that the optimal framework depends again on use case. So if you are serving long document or prioritizing throughput at a scale, TensorRT-LLM may be better fit. But if you are targeting fast interactive experience like chatbot, vLLM could offer better performance. vLLM versus DeepSpeed. So DeepSpeed recently actually just introduced this concept of fast gen, claiming that it can have up to 2x throughput improvement over vLLM. But there was like a kind of broader testing shows that vLLM often usually came out ahead in many real-world scenarios, especially those involving dynamic request size or more balanced prompt response length. vLLM was actually up to 1.8x faster. The key insight of this benchmarking is that performance is highly workload dependent. So again, based on the workload, some of these results may be different. Now let's talk about the Triton role in performance. So there was like a kind of another benchmarking which was done by run.ai, and one interesting thing actually just came out of that study. So when TensorRT-LLM was deployed on its own, it delivers actually strong result, but when it was paired with Triton Inference Server, performance improved significantly. So Triton play a critical role because of its advanced scheduling, dynamic batching, and the ability to handle high throughput traffic. So the big insight here is that inference performance is not just about raw speed. It's all about the system that orchestrates that end-to-end. And Triton brings the orchestration layer and enable a better performance as well. So when evaluating LLM, it is essential to understand those key metrics. So we've got these first time to token, or TTFT, which measure how quickly the model starts responding. There is another metrics as time per output token, or TPOT, which tracks the average time it takes to generate each new token and influence how smooth and fluid the user experience feels during long generation. And finally, we have throughput, which usually measure the token per second and tell us how much output the system can generate over time. So one thing that you need to understand and learn here is that there is no one single best framework or metrics across all scenarios. Performance depends heavily on the input-output length, batch size, request rate, and hardware setup. So what optimal in one context might underperform in another one. So benchmarking should always be aligned with your specific workload profile. So overall, here you can see some of these key recommendations. So the evaluation that you want to do as part of your benchmarking should be based on a custom benchmark suite. So and you can use any of those metrics that we discussed, like time to first token or time per output token. But then you need to consider 3 key scenarios. So low concurrency to assess baseline performance, and latency when the system is not under stress. High concurrency scenario, which tests how the system scale under pressure. And then variable length workload to simulate real world usage. By analyzing performance across these 3 main spectrum, you build a performance envelope that reflects your actual traffic pattern, enabling a data-driven decision. Now let's quickly talk about the decision guide, how you can choose those frameworks. So let's say if you have this low latency real-time API service, especially for interactive application like chatbot, we recommend vLLM as the primary choice. So vLLM is actually architectured especially for these types of use cases. Things like page attention, continuous batching are built to handle high concurrency while maintaining minimal latency. On the top of that, vLLMs offers a simple deployment path, which means you can plug it into the existing infrastructure very quickly. The second option would be Hugging Face TGI, which is also worth considering, and it's a turnkey solution that requires minimal configuration. Another case and another scenario is high throughput batch inference. Here, the main focus should be on maximizing token per second. So the primary recommendation here is the NVIDIA TensorRT-LLM with Triton Inference Server. So TensorRT-LLM use a compilation-based approach and is deeply optimized for NVIDIA hardware, offering the highest raw throughput. And when paired with Triton, you can gain orchestration layer that handles dynamic batching, request routing, and also resource management. Secondary recommendation is vLLM, which offers competitive performance with much simpler deployment process. And in short, if maximum throughput on NVIDIA is your goal, go with the TensorRT-LLM plus Triton. If you want strong performance with broader flexibility, vLLM is the option. Another case, multi-models and multi-tenant serving. And here the key is flexibility and efficient resource management. So again, our primary recommendation is NVIDIA Triton Inference Server. Triton decoupled backend architecture allow you to serve model from a variety of framework like PyTorch, TensorFlow, and more, all within a unified infrastructure. It supports dynamic batching, model ensembles, and offer robust scheduling. Secondary option is RayServe, which offers a more developer-centric approach, especially for team building custom ML workflow. Its Python native support fine-grained auto-scaling and integrates well with the broader Ray ecosystem. In short, for enterprise-scale multi-model orchestration, Triton is the go-to solution. For more custom composable pipeline in Python, RayServe is a strong alternative. When it comes to the fine-tuned LLM and complex architecture, especially those pushing the upper limit of model size, primary recommendation is this DeepSpeed Inference, which actually is built for scaling massive models. So thanks to its zero technology, which partitions parameters across multiple GPUs. This makes it possible to run multi-billion or even trillion parameters model that wouldn't fit into a single device. Secondary recommendation is NVIDIA TensorRT-LLM, which excel in cases where you are using mixture of expert model or other hardware optimized architecture. It supports expert parallelism and also is deeply tuned for NVIDIA GPU, making it a strong choice if your model architecture is complex but still GPU constrained. So if you are working with a fine-tuned or extremely large model, DeepSpeed is an ideal case. If you are leveraging NVIDIA optimized architecture, TensorRT-LLM offers the speed and efficiency. When it comes to the complex end-to-end application like RAG, where you need to combine multiple components, things like retrieval, generator, and possibly a re-ranker. We recommend RaySev as the primary option because it's built for orchestrating multi-step workflow that involves custom business logic. It allows you to define each step, like calling a vector database, pre-processing, routing to different models, all using Python native code. The secondary recommendation here is you can use the Python backend in Triton Inference Server. Why it may be less flexible for complex logic compared to Ray? It does allow you to define custom pipeline within the Triton environment. This can be a good fit if your organization is already standardized on Triton and you want to benefit from its mature MLOps tool. In short, RaySev is ideal for dynamic Python-driven RAG application, while Triton Python backend offers a more structured but still viable path for teams already invested in Triton ecosystem. The last case, when it comes to the edge, which is usually there is this cost constraint here. The primary recommendation is NVIDIA Jetson stack. Jetson is purpose-built for real-time AI at edge, such as robotics, drone, smart camera, and industrial devices. It got this Jetpack SDK, which offers a highly optimized software environment that brings many of the same performance benefits you are expecting from the data center class solution. Jetson devices also feature hardware acceleration for FP4 precision and also support a speculative decoding, making them compatible for running efficient LLM inference even in constrained setting. This combination makes Jetson actually ideal for real-time AI workload that need to be fast, local, and also cost-effective. So all in all, if your application needs to run close to the data, keep costs low, and also still deliver intelligent behavior, Jetson is the go-to platform. Alright, now let's quickly go through these key takeaways. So the most important here note here is that there's no universal best LLM 7 framework. It all depends on things like use case, infrastructure, and also team structure. So you need to often balance performance versus simplicity, and all these different options give you an idea how you can just run this trade-off and balancing. So future trend that you are seeing, it's clear that the LLM serving ecosystem is actually evolving very rapidly. We'll see continuous progress in low precision data type, especially FP8 and FP4, which are critical for reducing memory usage and increased throughput. At the same time, algorithmic innovation like speculative decoding are becoming also standard for boosting performance. Another major trend is the rise of fine-grained parallelism, especially for mixture of expert or MOE model, which activates only part of the model at a time. Ultimately, the frameworks that seamlessly integrate these innovations, from quantization, parallelism to memory optimization, will be the one that define the next generation of production LLM server. Final quick recommendation. So for team focusing on maximum throughput, low latency, both vLLM and NVIDIA TensorRT-LLM stand out. When it comes to the MLOps maturity and multi-framework support, NVIDIA Triton Inference Server remain the industry standard, as it decouples backend architecture, makes it ideal for organization managing diverse AI models. For those looking for simplicity, especially Hugging Face ecosystem, Hugging Face TGI is the option with minimal configuration. And finally, for complex ML application such as multi-step or RAG pipelines, RaySev shines with its Python native design. And last recommendation is all about the process that you need to follow, a 4-step process. You need to first evaluate your workload, clearly define what matters most. Is it latency, is it throughput, or model size? Your use case, and also whether it's real-time chat, batch inference, or edge deployment. Second, you need to benchmark the most relevant frameworks, so you don't need to solely rely on public result. instead test under your specific condition. And then consider operational factor. Look at how easy it is to deploy and manage these frameworks. Think about monitoring, auto-scaling, integrating to CI/CD pipeline, and so on and so forth. And finally, plan for future growth. Choose a solution that not only meets your current needs, but also scale and adapt to new hardware models and algorithms. So this is a strategic, actually data-driven approach that can help you to find the right saving framework for your large language model. Awesome. So that was all the content that I had for my presentation, and now we can open it up for question.